Again,
Good morning, everybody. I'm Marta de Simone. I'm a fellow at ISO in Garching in Germany, and I'm very happy to present here my work. So I thank the organizer for that. And I'm really sorry to not be there in person with you, but I'm very happy to discuss through all the virtual platforms that are available. Today I will talk to you about my work on the hot Corino nature in the perspective on the SKA and ngVLA facilities. In particular, before going to that, I would like to give you a first context showing you what are hot corinos. We are talking about low mass star formation, and that is here schematized in different stages. We go from a protostellar core that evolves into a protostellar one, then a protoplanetary disk, and then a planetary system. Right after the collapse, there is the protostellar stage, where we have that the central object is hot enough to sublimate the mantle of the dust grains. In this way, the gas is enriched of the molecular species that are trapped in the icy mantles formed in the prestellar space, and a new chemistry is triggered. So these hot Corino objects are formed and are defined to be compact, hot, and dense regions enriched in interstellar complex organic molecules, or ICOMs. In this stage, the chemistry is dominated by the ice mantle sublimation. However, we don't know if every protostars is really going through a hot Corino phase, and if in case also our solar system went through this very molecular rich phase. The hands of hot Corino started about 20 years ago, a bit more than that, were at millimeter wavelength. In particular, they were using facilities as the iron 30 meter single dish, and then moved to interferometric facilities as Plateau de Bure, now NOIMA, and ALMA. And this is mainly because the emission of these complex species is very bright at millimeter wavelength. Here, for example, we have an example of a synthetic spectra of one of the simplest ICOMs, methanol. And we see that more higher in frequency we go, brighter is the emission. However, we will see later that this was okay at the first stages, but now it's starting to be also a limitation. Indeed, now what we have after 20 years, that we have very, very few hot Corinos. Indeed, not every protostars possess a hot Corino region. We have about 25 ICOMs rich hot Corinos, but if we focus only on methanol emission, we can reach about 40. And these numbers are thanks to some unbiased spectral surveys done with ALMA and NOIMA. And here, for example, we have the first results of the ALMA large program FAUST, where we see that several protostars show very different spectra. So not only we have very few hot Corinos, but the few that we know, they are different from each other. Indeed, during time, classification has been done. We have some protostars that show hot Corino emission, but others that do not show any complex species, but rather sometimes they are very rich in carbon chains. In this case, the sources are identified as work carbon chain chemistry. I suggest you to give a look to the Eleonora Sbianchi talk that is right after mine. Therefore, why we have so few hot Corinos? Why they are so different from each other? There can be several possibilities. First of all, for example, we have observational biases, or the presence of small-scale structure that can shadow and hide the molecular emission, or a different grain mantle composition. These are just few examples, and I will show you. I will focus on the first and the last one because as I will show you, for answering to that question, we need to go to longer wavelength. We need to go to centimeter. So the first one that I tackled was the observational bias, in particular the role of the dust. Indeed, these objects are very young and embedded in their natural environment, so that the dust can be so optically thick to obscure everything. And in particular, if we manage to remove the veil of the dust, we see that actually the spectrum will reflect what we see. So when there is the dust, no unnoisy spectrum. But when we have removed the veil of the dust, if there are molecules behind, they just pop up. And to do that, we observed the IRAS-4A system where we have a binary system where one of the two, the IRAS-4A1, that is the brightest in millimeter continuum, do not show any ICOMS emission, while the IRAS-4A2, weaker in millimeter continuum, is very rich. And we targeted methanol, that was one of the brightest icons and the simplest icons precursor of many more complex species. And we looked at the VLA, so longer wavelength, where the dust is likely optically thin. And what we saw is that the methanol emission popped up. We are just seeing a hot corino that was hidden behind the dust. So this is a very important message that tells us that many hot corino can be actually hidden, and we are not seeing just because there is an observational bias. In addition, this raises an important warning that the emission of the several species can be highly underestimated at millimeter wavelengths, because actually also the abundances derived towards IRAS-4A2 were affected and underestimated by a certain factor, depending on how much the dust was absorbing. But this is not all. We have that we checked the first point regarding the observational bias, but still several hot corinos can show different spectra. And a possibility can be that they are reflecting a different composition in the previous stage, in the grain mantles. What does it mean? That given that the ice mantles are formed in the protostellar stage and then in the protostellar phase, what is in the mantles is released, setting the initial chemical content available for the hot corinos, then if this ice mantle composition is different, then we will have a different chemical, a different chemistry available. To do that, we should study the grain mantle composition, but is quite challenging for this object because they are deeply embedded and obscured for far infrared observations. So that's why we thought to retrieve the grain mantle composition indirectly. And to do that, we focus on the major components of the ice mantle that are here listed. And we focused on the methanol and ammonia that are the critical tracers. This is because they are the only tracers among this list that can trace only the central part without contamination from the envelope or other parts, and are easily observable with ground-based telescopes. And moreover, we can observe them simultaneously at centimeter wavelength using the VLA. And more importantly, we will know the information path, that they are very well studied from a chemical point of view, so we can retrieve from their abundance ratio the condition at the time of formation of these species. So these species are mainly formed in the previous prestellar phase, and in this case, their abundance ratio will depend on the condition of the gas, the cloud temperature, the density, and the formation timescale. To do that, we observed both ammonia and methanol, actually several lines. Here I show you only two for image purpose. And we saw that their emission is quite compact and among the three protostars. We have the IRAS-4A binary system and IRAS-4B, that is one protostar that is 30 arcsecond, almost 9,000 AU away from the binary system. And with a multi-line analysis and a non-LT approach, we derived the abundance ratio of these two species, and we found that the value for the three objects. And we found that the value were really comparable. That means that the three protostars need to have the same chemical history. That means that they were formed from a pre-collapse material with similar physical conditions. This is a very important result because it tells us something that we were not able to access. And to try to understand and to quantify this physical condition, we compared the observation with astrochemical models, in this case, the Gray-Noble model, and we could compare the ammonia over methanol abundance ratio prediction with respect to the temperature at different timescale and different density with the observations. We see that we could constrain only the temperature. That means that the condition at the formation of this species of the material was that the dust was at a temperature of about 17 Kelvin. But that is slightly too warm for a prestellar core. At these scales, we are talking about 60 AU. And in this case, if we were to look at the map of the region hosting this object, we see that this is typical for a less dense material of the region. That means that the protostars were formed when the cloud was still not so dense and so cold as we should expect. That means that something had to trigger a very premature collapse, so that the most of the formation time was happened when the cloud was less dense. So to conclude, I wanted to highlight the fact that these two main works showed the importance of centimeter wavelength on the study of hot corinos. Because first of all, we are going to longer wavelengths, we are not anymore affected by the dust opacity. So we are removing a huge observational bias. And not only, we can also go deep and study the ice mantle history of this object. But this was only a first step, and the next should be to move forward and study more objects in different star-forming regions, and to try to combine this multi-wavelength approach going to centimeter, millimeter, and infrared. But most important is that we need we are pushing the VLA at its limits now, so we need more sensitivity and high angular resolution together to observe more complex species than icons, so to have a complete spectral survey at very small scales, about 10, 50 AU. In different sources and different regions, so we can hope also to a complete survey of this. And ngVLA, the combination of ngVLA and SKA is crucial on that point, because we will have a full coverage of the entire sky with northern and southern hemisphere, but also a very wide frequency coverage, because we need both. And here I show you just fast what I mean for the spectral coverage. We know that the brightest emission of the icons is for sure in a millimeter, but that means that a millimeter we are starting to have a lot of sensitivity, so we are limited by the line blending at the confusion limit. We are limited now by the confusion of the spectra. So going to longer wavelengths, first of all, we will reduce this confusion limit. And most important, moving to longer frequencies, the emission peaks of more complex species, it will be shifted. So we can hunt and search for more complex species to what we have also the simplest amino acid, like the famous glycine, that is always looked for. And so combining centimeter and millimeter, or in any case having a large frequency coverage, will allow us to correct for the dust absorption factor, to give a complete chemical census and have a strong multi-line analysis to derive the physical properties of the gas. And with that, I thank you for your attention, and I'm happy to take every question you may have. Thank you.
Okay, and Marta is online and ready to answer questions?
Yes.
Great. So questions from the audience? I mean, I do have a question. Personally, I work on a completely different field, of course, but for galaxies, we always talk about the importance of environment in the evolution. So is there a particular effect of the wider environment of the molecular cloud where these corinos happen on the composition or the presence of the corinos themselves?
Okay, so there are some studies that are trying to investigate that, especially on the when a source is not isolated, or if it is part of a more crowded environment, especially on the difference between the two kinds of protostars that I first mentioned at the beginning of the talk, the hot corinos and the WCCC. So there are some studies by Bouvier et al. And others that are trying to investigate that. Especially in Orion, that is a very well-known protocluster, so where we have a external illumination from one side, so there is a study ongoing on that. So far, nothing is clear about this interaction, but yeah, it's an ongoing study.
But you see higher frequencies of these sources, maybe in some clouds than in other clouds, for example. So
I'm not sure if I understood what you mean.
Well, I mean, are corinos more common in some clouds than in other clouds? So where you have a number.
Actually, there was a comparison between the Perseus cloud and the Orion cloud, and it looked like there was a small difference. But yes, that this is oranges, the program done in Orion, and peaches done in Perseus. So it looks like they are different.
Okay. Thank you. Okay, questions over there? Manasseh?
Thank you for your interesting talk. So you said that the three protostars have similar chemical history, right? And said that the temperature must have been warm, like more than 17 Kelvin. So what exact chemical reactions, or like the abundance of, so which species determine this temperature?
Okay, so the species that I used were methanol and ammonia, because they are well studied and they are mainly grain surface species. But for ammonia, there is a gas phase counterpart that acts. And their abundance ratio depends on the physical conditions. So we studied the various chemical pathways of these two species. And we saw that to reproduce the observations, the temperature should have been around 17 Kelvin. Yes, so I think I'm thinking about the question again. So these were the two species, and we saw that the abundance ratio of methanol and ammonia in the three protostars was the same. So that was suggesting that their origin should have been the same. This is because this abundance ratio directly connects the physical properties of the pre-collapse phase. Because right after we expect that what we see in the gas comes directly what was in the dust in the previous phase before the collapse.
Okay, thank you.
Okay, so let's thank Marta again. And
many thanks.